Ever wondered how computers sort data so quickly? Welcome to an enlightening discussion about the MergeSort algorithm. This powerful tool is one of the many algorithms that computers use to organize and make sense of the vast amounts of data they handle every day. Sorting algorithms, like MergeSort, are the unsung heroes of computer science, working behind the scenes to bring order to chaos. So, why MergeSort? It's not just that it's efficient, though it certainly is. MergeSort is also stable, which means it preserves the original order of equal elements, a quality that can be crucial for certain tasks. It's like the reliable friend who not only helps you move, but also makes sure your fragile items are handled with care. By the end of this video, you'll have an in-depth understanding of the MergeSort algorithm, so buckle up and let's embark on this journey of discovery together. At its core, MergeSort is a divide-and-conquer algorithm. This is a phrase you'll hear quite often in the world of computer science, and for good reason. MergeSort is a powerful sorting algorithm that uses this approach to sort lists of data. So, how does MergeSort work exactly? Well, it all begins with dividing the data. Imagine you have a list of numbers that you want to sort. MergeSort doesn't try to sort the entire list all at once. Instead, it breaks the list down into smaller, more manageable pieces. It keeps dividing the data until it ends up with multiple sublists, each containing just one element. You might be wondering why we would do that. It's because a list with only one element is, by default, already sorted. Now that we have our sorted sublists, we can move on to the next step, merging. This is where the magic happens. MergeSort begins to combine, or merge, these sublists back together. But it doesn't just randomly slap them together. No, it merges them in such a way that the resulting larger list is also sorted. This is done by comparing the elements of the sublists and placing the smaller element first. This process is repeated until all the sublists are merged back into a single sorted list. And here's the really cool part. MergeSort does all of this not once, but repeatedly. It's recursive. That means it applies the same divide and merge process over and over again, each time on a smaller piece of the data. This recursive nature is what makes MergeSort so efficient and powerful. So, in essence, MergeSort is a three-step dance: divide, sort, merge. First, it divides the data into smaller pieces. Then, it sorts these pieces by merging them back together in a specific order, and it does this over and over again until the entire data set is sorted. So, it's a matter of dividing, sorting, and merging. Simple, right? With a little bit of practice, you'll be doing the MergeSort dance in no time. Now that we understand the basic concept, let's delve deeper into how MergeSort works. Imagine you've got a messy bookshelf with books of various sizes and topics all jumbled together. You want to sort these books by size, but how do you go about it? The MergeSort method would have you first divide the bookshelf into two halves, then divide those halves again and again until you're left with individual books. This is the divide phase of MergeSort, where we break down the problem into smaller, more manageable ones. Now, let's say each book represents an element in an array. In the divide phase, we keep splitting our array into halves until we're left with single element arrays. These are, by definition, already sorted. You can't unsort a single book, can you? Alright, so now we have a bunch of sorted single element arrays. It's time to put our bookshelf back together. This is the merge phase of MergeSort. We start by comparing the first elements of two arrays. The smaller of the two gets to go first, while the larger one waits its turn. This process continues until all the elements in both arrays have been sorted and merged into a new, larger array. But we're not done yet. We've got more books to sort, or rather, more arrays to merge. The process repeats, comparing, sorting, and merging until all our single element arrays have been combined back into one, now perfectly sorted array. This is the beauty of MergeSort. It takes a seemingly complicated problem, sorting a jumbled array, and breaks it down into simple, manageable tasks. It's like cleaning up a messy room by focusing on one small area at a time. Before you know it, the whole room is clean. And just like that, your data is sorted, but how does this happen in code? Coding the MergeSort algorithm might sound challenging, but it's easier than you think. Let's break it down into three main parts: divide, conquer, and merge. We'll start with the divide part, where we split our array into smaller sub-arrays. Imagine we have an array of 8 elements. In the divide phase, we keep splitting this array into halves until we have 8 arrays of 1 element each. This is accomplished using recursion, a concept where a function calls itself within its own definition. In code, it would look something like this. We create a function called MergeSort that takes an array as input. If the array has more than one element, it calls itself on the 2 halves of the array. This is the recursion part. It keeps calling itself until it's dealing with arrays of 1 element. Next, we have the conquer phase, which in the context of MergeSort is a bit of a misnomer, as we're not really conquering anything. We're just sorting the individual arrays. Since these are single element arrays, they're already sorted. The real magic happens in the merge phase. In the merge phase, we combine the sorted arrays back together, but in such a way that the resulting array is also sorted. To do this, we create a helper function called merge. This function takes in 2 sorted arrays and compares the first elements of each array. The smaller of the 2 is removed from its respective array and added to a new array. This process is repeated until both input arrays are empty, resulting in a sorted array. Let's put these 3 parts together in our MergeSort function. First, we check if the array has more than one element. If it does, we split the array into 2 halves and recursively call MergeSort on these halves. Once we've broken down the array to single element arrays, we start merging them back together using our merge function. We do this by calling merge on the results of the recursive MergeSort calls. This is a recursive function because it keeps calling itself until a base condition is met. In our case, the base condition is an array with a single element or no elements. It's a classic example of a divide and conquer algorithm because it breaks a big problem, sorting a large array into smaller, more manageable problems, sorting single element arrays, and then combines these smaller solutions back into a big solution. So there you have it, the recursive nature of the MergeSort algorithm implemented in code. We've gone from a high-level overview of how the algorithm works to a line-by-line breakdown of the code. And remember, like any other algorithm, understanding MergeSort is all about practice. So don't be discouraged if you don't get it on the first try. Keep coding, keep trying, and you'll get there. There you have it, the MergeSort algorithm in code. But let's recap to make sure you've got it. Let's take a moment to summarize what we've learned about the MergeSort algorithm. This elegant piece of computer science is a divide and conquer method that sorts a list in a time-efficient manner. It's all about breaking down a problem into smaller, more manageable parts, and then putting them back together in a sorted order. We started by splitting our list into 2 halves. This division process continues recursively until we have multiple sublists, each containing a single element. Now, these single elements are inherently sorted, aren't they? That's the beauty of divide and conquer. Then we dove into the merging process, which is where the real magic happens. We compared the elements of our sublists, picking the smaller one first and putting it into a new sorted list. We kept doing this until we had exhausted all elements in both sublists. If one sublist finished before the other, we simply added the remaining elements from the other sublist to our sorted list. This merging process too was performed recursively so that we eventually ended up with a single sorted list. One of the key advantages of MergeSort is its efficiency. It's got a time complexity of O log n, which means it scales pretty well as the size of the list increases. It's also a stable sort, maintaining the relative order of equal elements, which can be quite important in certain situations. We also had a look at the actual code that makes this all possible. Remember, the key functions were MergeSort for the division and merge for the, well, merging. With just a few lines of code, we were able to implement a highly efficient sorting algorithm, and that's MergeSort in a nutshell. Next time you're faced with a heap of data, you'll know exactly how to sort it.